So good afternoon, everybody. My name is Antonio Castello. I'm technology manager at Epic, and it's time to start a new chapter in our famous online technology meetings about photonics technologies for different markets and applications. And the topic today is quite interesting and exciting. So it's photonics for thin films, fabrication, and characterization. Coatings and thin films are being used in really a lot of different markets and industry nowadays. So we thought that it was very interesting to have a summary of new and different fabrication techniques, what is missing in some of the markets as well, and understand characterization tools that are being used nowadays and proposed nowadays by Epic members to characterize the thin films and the coatings. And for those of you that are not Epic members, just a short summary about the Photonics European Consortium, European Photonics Industry Consortium. This is Epic, the more than 800 members, all of them companies and a few research centers that are related with the photonics business. And our goal is to ensure the sustainability of the photonics business. We want to help our members to find new partners, to find new collaborations, to understand about new markets. As you can see in this summary of the benefits that we offer to our members, the idea is to, as far as we can, help all the companies with their technological needs. So find new suppliers, find alternative technologies that can be interesting in their manufacturing process. Also have access to market reports where experts in different topics can summarize the trends in the market, the figures for the next years. This is something that is available in our extranet for all the members. We help also with access to markets and mentorships. We support the human resources activities and investment, so we can put in contact small companies in the reach of money with investors or venture capital companies, and also networking. So these kind of meetings that we are having today is kind of technological information, so you are going to understand what is new, what is the trend in this thin films fabrication and characterization. And there is also the opportunity of having networking, not only during the question and answers, but also afterwards. If there is somebody that you see in the room that you want to be connected with, you can contact us and we will introduce both of you by email for further discussion. I mentioned these networking activities and the technology, and we are having more of our events, both physical and online. So I encourage you to go to our website. So we will continue doing online technology meetings. For example, next one's in Photonics for Vision and Eye Research, and also in July about sea exploration and oceanography. And we combine with, as I mentioned, human resources work groups, also with marketing meetings to help your marketing team to find new ways of promote your company, and sustainability work group, where we discuss with companies that are involved in the sustainability process to see what's the trends, what are the advices for companies that are already in this journey. And of course, physical meetings. So you see here a summary of the ones we will have in May and June. So we go to Expo to talk about photonics for XR, to Berlin about photonics integration and packaging, hosted by Fraunhofer ICTM. We are going also to Photonics Bretagne in Lannion in France to talk about the specialty optical fibers. And we will continue in September with Photonics for New Space during the ESA Industry Days in the Netherlands, Photonics for miniaturized optics at Sony DADC in Austria. And of course, we will be present in the ECOC conference in Frankfurt. So we'll have a VIP network and reception, other activities. So if you plan to attend this meeting and this conference, check the possibilities to network with other members and other companies in our website. We also are involved in different European Union projects where we are in charge of the dissemination and communication activities and work packages. In this case, I would like to highlight the Pulsate because it's one project that is related with advanced manufacturing and advanced and additive manufacturing, and coatings and thin films can be related with this topic, and the expertise of departments could help you in your needs. So in case you're interested, please contact me back to discuss your potential need about use laser advanced and additive manufacturing for your manufacturing process. And yeah, let's go with our sponsor today, because our meetings are nothing without our sponsors. So I would like to thank Spectrogon, that is the company that are sponsored the meeting today. And we have one slide that Herman, you can perhaps tell us a little bit of what is your company and your activities.
Hello, everyone. Greetings from Stockholm, Sweden. Just a short reminder from us here to all of you that we exist. We are happy to take calls with you and progress in the field of evolving in the thin film manufacturing. We are a one-stop shop for coatings between 400 and 15,000 nanometers. We're growing quite big. We are about 90 full-time employees now. And as I said, we see ourselves as a one-stop shop for coatings, windows, substrates, assemblies, filter wheels, VLPs. We have a full 200 millimeter wafer line. I think we are quite strong in customizing geometries, everything from 1 millimeter to 200 millimeters. Really investing a lot into data-driven quality assurance and supplying our customers with full data sets of what they're purchasing. And for universities and research, we really encourage you to go to our website at spectragon.com to explore low volume batches for your testing. And of course, we are very proud that all these amazing images that are coming from the James Webb Telescope, as you see in my slide here, are taken with our filters. That's it. Looking forward for the discussions today.
Thank you, Herman. So I encourage everybody which can be interested in any of the capabilities of Spectragon to discuss with Herman. You have also the chat and here where you can place questions directly to Herman. And thank you for being the sponsors in our meeting today.
Thank you.
And we continue with the supply chain. That is one slide that we create with all the companies that are registered to this meeting. And it's quite interesting to see the amount of different companies that are interested in this topic, different end users and integrators covering from defense to optics for automotive industry, for example, different manufacturing equipment manufacturers, both in laser, optical components, also filters. So really a broad amount of companies that are interested in the topic today. We will place this slide in our website after the meeting. So I encourage you also to go back and check all the companies and people interested and find somebody that is interested for you to be connected with. And let's go with the agenda for today. So we have 5 really great presentations from IMEC, Land 3D, the TII in Abu Dhabi, Lightech, Das Nano, the Buehler Group, and Essen Optics. And I will start introducing Philippe Susan, that is a program director of Sense and Actuate Business Unit at IMEC. And he's going to give us an overview of the photonics and optics manufacturing platform at the center. So Philippe, the floor is yours.
Thank you very much for the introduction. Okay, so quickly about IMEC. We are an R&D institute that also perform low volume manufacturing. Essentially, we cover all the TRL level that can be possibly made with this nanotech technologies. We are about more than 5,000. We have been growing considerably. We are now more than 5,000. Most of our revenues are actually out of industry. And we have 2 sites, one on 200 millimeter, one on 300 millimeter, and the 200 millimeter site is more dedicated for the most mature activities, including photonics and optics. But we are also expanding these activities in the 300 millimeter. So the infrastructure that we have on the 200 millimeter is based originally from a CMOS baseline 0.13. The 300 millimeter is more advanced, 65 to 28. We are, of course, well known to other people for the most advanced CMOS scaling, but I didn't put it on this slide. We are operated 24/7, and we have all kind of integrated photonics and flat optics type of technology together with the ability to manipulate different kind of substrates such as glass substrates. So when we look at our different platform, we essentially have pixels. So this is the active part. We're doing photonic, nano optics. We're also covering MEMS, 3D, and so on. And today, I will talk to you about meta-optic, multispectral, silicon photonics, silicon nitride photonics. We do have as well some activity on nano imprint lithography that is somehow related there, but I didn't have the time to cover that today. So when we look into what are we doing, essentially we are trying to manipulate light either by a form of a waveguide. So this is the yellow part. We try to couple in waveguide. There are some active functions, either detections or lasing, that eventually occurs in such a way, or we can also manipulate the light in the Z direction. So this is essentially the difference between integrated photonic and nano optics. And there are for us critical aspects in terms of coatings and thin films. First is the feature size. Obviously, when you want to manipulate the light towards the lowest wavelengths, then things tend to be very small, specifically for meta-optics. The refractive index, in order to have a good core, the transparency is important. So at which point do you decide that you have a waveguide or not? It's actually a perpetual debate in the organization, believe me. But essentially, that's what it's coming down to, the transparency. And what we do care as well, which is somehow related, is the line edge roughness, or eventually the surface roughness of the coating that we are using. So when we talk about integrated photonics, the most popular technology that we have is our integrated silicon photonics platform. It's based on crystalline SOI silicon. We do have as well LPCVD silicon nitride waveguide that can be integrated together with the platform. The platform is very complete, actually has been developed in our facilities, has been transferred to a production site where our PDK is running. And these are the people at the end that care the most about the control on thicknesses and on refractive index in the organization. There are other specific layers like germanium and so on that we are growing by epitaxy, which also need some careful processing. This is this first platform where you can see we are stacking the SOI, we are putting the silicon nitride, and then we have back-end of line type of processes that we are running. We also have a low-loss silicon nitride, and that one is the high-temperature nitride, which go into dB per meter range usually. So for some application, specifically in quantum, they are really chasing the photons. And we do use this platform for this kind of application where the losses are extremely important. For meta-optics, for those who are not familiar, the light propagates in a Z direction through the surfaces, and you are able to achieve different kind of function. So lenses is a very classical one, so flat lenses in that case, but you can also do color filtering, you can do beam shaping, you can also use it for doing some kind of a beam steering, shaping, display expander, and some people can also use it as a reflector. So the platform is very versatile, and it relies on this specific sub-wavelengths resonances that actually occurs in the structure. We are using different kind of materials for that, starting from the low index, silicon oxide and quartz for the substrate. And then there is a lot of work going on doped glass when you're actually using the core of the glass also as a waveguide. So that is very popular in AR/VR. But we are also looking into the highest index material, niobium oxide, titanium oxide, and even amorphous silicon. They are, of course, not all transparent in all the wavelengths, but that is what you need to do, for instance, when you are operating in SWIR or above 900. We use the silicon because it has the highest index. Otherwise, we start to use a material like titanium oxide and niobium oxide. They are slightly different. There is perpetually a lot of debate in IMEC and why we should use one and not the other one. And to cut a long story short, niobium oxide might be a bit lower in index, but actually is much more stable when it comes to temperature. And titanium oxide can still buy you some performance if it's processed in the right manner. We have been processing this different kind of structure. So with the silicon nitride on glass substrates. So these are structures that are either directly processed on the glass or that are actually layer transferred onto a glass. We do the work for niobium oxide and amorphous silicon. Here you can see some example of 200 millimeter wafer that have this flat optics type of structure. Another important item today, so we are post-processing imager wafer with Fabry-Perot type of structure, so thin film interferometers. There, we are not going to rely on one or two layers, but clearly on a stack of very different layers where the uniformity, actually the optical path is extremely important. This is something that we do in the organization. So each of these small block that you see there, you can see all the layer stack, is we coming and we are directly on the pixel processing a stack of thin films. The deposition is very important. We are working with Buller actually on the topic. I see they are later in the call. I think they'll be happy that they are cited here. But we do as well have, depending on the wafer size, other kind of equipment that we use. This is helping us to provide different kind of structure. So we have line scan, we have classical imaging with Bayer-like patterns. Depending on the wavelengths that you want to sort, we apply some different kind of processes. And the control on all the layer thicknesses is extremely important because the direct physical thickness is going to determine the wavelengths that you're going to filter. So here a classical example of some filter material where we achieve about 90% of transparency at 400 something nanometer. You can see this is a typical layer stack that is being used. So the layers are not always uniform. We are sometimes doing some custom made thicknesses. We can etch quite straight. So the etching, I know we are not into an etching meeting, but actually once you have the good layer control, etching this material is also extremely important. And so far, this is what we can achieve. In general, etching very dissimilar material, classically in semiconductor manufacturing, it's a challenge. So we are also, welcoming input from the H2 vendors as well. As a conclusion, I've been running a bit fast, but I'll leave a bit of time for question. The first thing that comes to our mind for coatings is tight thickness and RI control. So when by tight thickness, I mean usually less than 1%. Well, this is really important. And actually, classical tools used in semiconductor manufacturing are a bit looser. They are also producing layers that sometimes are a bit more rough. So that's really a point where we are thinking for major improvement. When you go towards the edge of the wafer, usually this is where the machine vendors have not always been designing that so carefully. But rest assured that the etching guys have also been giving away the last centimeter of the wafer usually. At least on 200 millimeter for the older generation tool, on 300 things are a bit better. And which is also very important for us is the refractive index control. Some people don't always mention that, but having a very uniform control is nice for the thickness, but actually what matters is the refractive index, and there we are into 0.00x, even better than that. That is extremely important. So for instance, when you're forming thin films and there is slightly different microstructure, a bit more of crystalline phase or a bit more of an orientation, we will be quote unquote seeing that in the performance of the devices. And that is something we are watching very carefully. Now, the next generation of material, moving to the next point, we see today this industry has been, so for integrated photonics, they have been concentrated on crystalline silicon, polysilicon as well, amorphous silicon. Now they are going towards silicon nitride. These are materials that are quite interesting. Disadvantage of nitride is that contrary to silicon, you cannot produce active with it. So for the silicon nitride, we're also looking at adding new kind of material property. In the world of optics, there clearly we are relying on the refractive index contrast. So you need to be able to deposit very uniformly these thicknesses. You need to be able to pattern them. We are talking about pillars technology. So it is very common that you need to have several hundred nanometers of thickness of a layer and sub 100 nanometer pillars. And depositing the layer, being able to etch it is very important. And then you have the next step, which is you need to put oxide, the lowest index material. You need to be able to do gap fill. And that oxide, it's not very often cited, but sometimes induce as well optical losses because the people that work on these depositions adding a bit their ingredient, the precursors and so on that are typically used in CVD processes, they also induce losses. Niobium oxide, titanium oxide, very important for us for the upcoming platform. We have been demonstrated niobium oxide as well as a waveguide. So the losses are not yet at the level of what we can reach with silicon nitride, but are today maybe in the range of what you can do with crystalline silicon. We are also seeing region of the spectrum that becomes more and more interesting. So the aluminum oxide for the UV transparency is very important. And we see these three kind of material really coming up. So for all the people that are working on coatings and characterization of these coatings, this is definitely an area of interest for us. Now it's maybe it is a bit out of scope, I don't know, but just want to mention that. So as I mentioned, only silicon is active. So when you apply the bias to it, then it can do things that the other material usually cannot. So we are looking to new kind of electro-optic material like thin film lithium niobate, barium titanate. These are more crystals. We actually need to have a crystal to produce the electro-optic effect. These will also require very tight control. So the thin film lithium niobate, normally it's an ingot that you slice and you eventually bond into something else. The barium titanate is today an MBE process. So it's very expensive, but it produces tremendous performance. I think there's plenty of work to be done for this audience as well for this material. Thank you for listening to me.
Thank you very much, Philippe, and also thank you for summarizing some of your needs and interests also for the future. We have time for questions, so you can raise your hand and make your question directly to Philippe. You can also use the chat and the Q&A box. So any question from the audience? Yeah, Amir. You are muted, Amir. We still don't hear you. No, not yet. Perhaps you can write it, Amir, in the chat. Yeah, Joan.
Can you hear me? No. Can you hear me? Finally.
I can hear you.
Fantastic. So thank you, Philippe. This is an amazing work. So quick questions on this sort of novel crystal, especially TFLN. I mean, are we looking actual growth of it or this is more like a transfer printing?
Yeah, so of course, IMEC, we are biased by our past, which is we like large wafer sizes and specifically silicon. We are not at all looking into the growth, but yes, we are looking into transfer printing or other forms of bringing thin layers onto the larger substrate. For us, we look at it with an heterogeneous integration mindset. But once this layer is transferred and you want to measure its thickness, for instance, to know if you have the right material being put on your 200 or 300 millimeter wafers. How do you do that? So that's a question.
Okay, thank you.
Okay, Joan.
Yes, thanks for the presentation, Philippe. I have a question. You mentioned the tight control of index of refraction. Are you looking to measure the absolute value of the index of the material you are using or you're depositing? Are you looking to map the change of index over an area?
So actually, it's a good question. In practice, we run material, we do wafer level scans, and we take that to build our library. So of course, the variation within the wafer is very important. I don't think so with the silicon nitride, things can drift quite easily. With silicon, we never had to ask the question ourselves whether it would vary. But for silicon nitride, yes, we do see that it can absolutely vary, not only, change locally, depending on the processes. It is very clear that the process, high temperature nitride will be more uniform than something where you can sometimes see the imprint of the shower head of, say, a PECVD equipment. So yeah, I'm not able to answer your question, but ideally we need indeed the absolute control.
Okay, thank you.
Marcelo, you placed your question, but you can do it live.
Yes, my question was again about the control. You're talking about also a epitaxy and etching processes control. What kind of accuracy are you targeting there?
I'm sorry, could you repeat the question a bit louder? I didn't hear you well.
I mean, epi and etching control. What kind of accuracy are you targeting there?
So for the etching control, well, so we use our advanced lithography usually for waveguide. So we define objects that have down to 70 nanometer in width, if you can call it like that, lines and space. So when we are etching, we are looking at angles that are as straight as possible, or at least if they are varying, we would like to make sure that this is uniform. So we are really looking into these kind of things. The way we do it usually is that with the CD-SEM, we'll focus on the top, we'll focus at the foot, and we'll get somehow the angle together with some cross-section that we ran during the development.
I don't know if there is any other. Yeah.
No, it's
I don't know if there is any other question for Philip. Yeah, Mihai from Hailase.
Yeah, hi Philip. I was just wondering, what is the minimum amount of wafer or optics that you could produce for a single customer or a cooperation partner?
Yeah, so in our facility, as it stands today, we can do 1,000 wafers per year, which, depending on the amount of dies that you need, can be very large. And as you know, we are also, it's public, we are opening a site in Malaga in Spain, and this will be a place where we will have 300 millimeter capability to do even larger volumes there. Now, of course, we don't have the mission to become a foundry, high volume foundry. We'll never compete with TSMC, to be very clear. But in this space of optics and photonics, things are low volume by definition so far. So if one day there is not enough demand, despite the few thousands of wafers that eventually we'll produce, we'll be happy to transfer our process. We can also transfer our process even today to manufacturing sites of your choice. This is maybe a discussion we should have in a separate moment.
Okay, thank you very much.
We have final question, Tanduy from Silicon Austria Labs.
Hello, thank you very much, Philip. Very, very nice presentation. Just a question about the materials. From the perspective, could you share with us any strategy on infrared materials? Because so far, we try to move also to shorter wavelength, but on the other side, it's infrared really attract interest here.
So you have probably seen that we have germanium. So yes, we have some work going on with germanium for the mid wave and long wave. This is a material that we are looking at. But germanium, the issue is that, so we are growing it by epitaxy for our detectors today. It's a bit slow, it's a bit complicated, and usually you're using silicon as a clad in that wavelength regime, so it has its own challenges. I think it's still on the research side at the moment. We'll be happy that one day there are germanium substrates that are germanium, slice bonded on silicon. We'll be very happy to access this material produce the waveguide system. I didn't show it there, but yes, we do have some activity about that, but it's really not what I will qualify as a platform today for us. So it means we take guarantee that things are working as we do for the other technologies that I'm showing here.
Thank you.
Thank you very much, and thank you, Philippe. Thank you very much for the nice discussion and nice presentation as well.
Thank you very much.
So we can proceed with our next speaker. I want to introduce you, Maxime Plakogniuk. I probably didn't say it right, so Maxime, I'm sorry for that. From the company Atlant 3D, founder and CEO, and he's going to present the advanced optical control through the direct atomic layer processing. So Maxime, the floor is yours.
Thank you, Antonio. I think you did a great job.
Thank you.
Yeah, my surname is a half letter, should be removed. It's a transliteration from Ukrainian.
And I'm Spanish, so for me it's even more difficult.
Yeah, that's fine. So pleasure mine today to present. Thank you for inviting, and thank you for giving the opportunity to present the company. Atlant 3D, we are based in Copenhagen. We develop unique technology, direct atomic layer processing technology. It's a modification of atomic layer deposition, ALD. So typically ALD done on a whole wafer. We do this locally, and we are based in Copenhagen. We have about 35 people with a focus on different applications, but primary focus is optics, photonics, and microelectronics, and emerging applications. So how we do today micro devices, it's through lithography, so multi-step, different either deposition or etching and patterning. So it's, my opinion, quite complicated. So we decided to combine ALD with additive manufacturing approach, and having benefits of both. So growth of various material, control at atomic scale, bottom up, digital control over the printed features, and so on. And coming to ALD, there are two methods to do this. One is temporal ALD in a vacuum chamber with pulse by pulse processing. I believe I don't need to explain much about this. I believe many of you are engineers and know what is ALD, but there is another way to do spatial ALD, which can also work at atmospheric conditions. It's like a print head with the slots for each precursor and reactant to be delivered in separate zones, and then the substrate underneath moves and the deposition happens. So what we did, we made the micro nozzle, which has a centric geometry, and through this geometry we deliver ALD precursors to the surface, and one motion gives one atomic layer at a time. And this micro nozzle, it's about 16 by 16 millimeters. It's a microchemical ALD reactor, which is also replaceable. It can be different configurations of the nozzles, and the resolutions provides us a local ALD process. And here you could see this was our first article published in 22, where each letter was deposited with different thicknesses. As you could see, a lot of artifacts at that time. We already fixed many of them. And what we didn't expect is conformal and also very abrupt deposition, as you could see here from the lines of the process. And this basically gave us a possibility to control at atomic level each material and obtain patterns of any shape. So today the technology has several critical capabilities of direct patterning, local deposition, broad selection of material. It doesn't require vacuum, but we also work in vacuum. Micrometer scale line width. We recently demonstrated few micrometer line width. Since it's ALD, it can work on very complex surfaces, not only flat wafers, but membranes and nanostructures. And it allows also processing across the whole value chain, from material processing to scalable manufacturing. So with this technology, we build an equipment and we compare this equipment as either can be integrated in the clean room, but also can substitute some of the processes. And we already validated deposition, of course, and then recently we demonstrated local etching. And we're looking now for local doping with our technology. And the equipment that we're building, it's integratable for glass boxes and cluster tools. So easy to work with existing infrastructures. So from our technology, as I mentioned, we do deposition, we do etching, we're looking into cleaning and doping, and then various applications that can be derived and built on this technology. We focus now on RF, printed electronics, sensor actuator MEMS, optics, photonics, advanced packaging. We now working on anamorphic sensing. Some quantum applications started to work, but the critical and the most interesting for us, it's a sensor and optics, 2 areas. So we work from material testing with very fast design of experiment to process structures, devices, and systems, including heterogeneous integration possibilities. So this is a list of materials that we have been validated. It's actually more than 15 now. This is the one that we have confidence that we can reproduce. A lot of other materials we are testing still, so I'm not advertising them. Mostly it's oxides. IMAC mentioned, I forgot who was that, sorry. Don't want to be impolite. So aluminum, titanium oxide, zinc oxide, iridium, hafnium oxide. We recently demonstrated gallium oxide and planning for niobium oxide also within the next month. What we do with this technology, we have flexibility in the thickness control, geometry control, gradient thickness control, roughness control, so we can easily modulate roughness. As you could see, this is comparison of 2 surfaces which we rastered. So this is completely flat with nanometer precision. This is with structures. We easily do have a flexibility over process development, so variation in the thickness, as you could see, from 5 nanometers, like 200, and the same wafer variation in the different temperatures that could be deposited. And this is one of the examples of these structures were deposited on the same element. You might ask, well, how much time it takes to process? Depends, of course, on the micro nozzle, but 1 millimeter square, for example, if it's used with 360 micrometer nozzle, it takes like 1 minute to deposit, or 50 nanometers, 6 minutes. And the nozzle can be made like for 1 centimeter, also 1 centimeter wide. So it also would take 1 minute, but for 360 micrometers, it's like 40 minutes. So surface structuring, it's one of the key capabilities. So here you could see step-like gradient. It can be flat gradient, so very straight, or this type of structures. We can deposit over different type of surfaces. So here you could see silicon microgratings. This is black silicon. This is porous material. And this is just overview what type of surfaces we already deposited on. So random, micro, like membranes, or curved surfaces like for optics. One of the very interesting results that we recently obtained is by printing variable vertical, horizontal lines, we obtained the like squares, as you could see here. And by varying different thicknesses, you could see different squares were achieved with different geometries. And the next, what we did, we tested this to basically modulate refractive index. So by varying geometries, not the material, we achieve different refractive index changes. So this is just overview to give you an idea what we did recently. So this is a direct rastered approach for hyperspectral gradient elements. This is 2 similar wafers that we did development with variation of the thickness of gradient of the thickness. This is for sensing elements like electrodes. This is for gas sensing. This is for electrochemistry. So we're looking into the areas where our optical capabilities or optical material capabilities can be used, like for optical filters or for hyperspectral or for metasurfaces or for waveguides. And we can work on any type of substrates, not only silicon, glass, polymers, or gallium nitride or silicon carbide. It really doesn't matter. ALD is quite flexible in that sense. And the capabilities that the most interested is in optics and photonics. So just to highlight the development that we did with the gradient thickness filter, this is how we did. So we made bigger squares with one thickness, then we reduced the area for rastering to 5 nanometer thickness, 10 nanometers. We can really control it. It's like overnight process where nobody is engaged. We just leave it and the machine does the work. And in the end, you could see here the control over the thickness. We did the test measurements that confirming what we wanted to achieve. We did this with titanium oxide, but it can be done with any type of material, including metals, or like say there was a previous speaker interested in niobium oxide. Another very interesting test that we did. So metasurface and the surface modulation, basically. As you could see here, there are two functions that we implemented. One, it has this type of shapes. I don't know how to call them. Another was with just peaks. They can be as even as well as uneven, and it really depends on the geometries. And we, again, this is in automatic mode that we did. We did these measurements with imaging ellipsometry just to confirm that we obtained what we expected. Another development that we did recently with Silicon Austria Lab, it's local deposition on micrometers, where the request was to localize the titanium oxide in this area. It was actually successfully accomplished. So basically, working on a very sensitive diaphragms or any other very sensitive elements is quite also easy for us. We pre-program the area that we need to deposit, and then the printhead goes in that area and does the deposition. Another element which is less relevant to optics, but can be also applied, it's a heterogeneous sensor integration. You could see here all elements were done with the same process flow, electrodes with platinum, and the sensing element with different thicknesses with titanium oxide in one run. And how we do this, we have now nanofabricator light, our core equipment, that's we also promote now, and nanofabricator pro. It's a 200 millimeter tool that we have the prototype in-house. That's what we use for development, and we finishing the industrial tool end of the year. And we just finished recently nanofabricator hub tool, which is which is staying in Switzerland with our partner in Lausanne. So happy to engage you. So how we work with equipment sales and also providing innovation as a service, so engaging with customers, providing from pilot to R&D, joint venture, joint development, or public funded projects, or contract manufacturing. And I would be happy to discuss any questions, and let me know if there are any interest to explore here.
Thank you very much, Maxim. And you also have here the email address in case you want to contact Maxim afterwards for any discussion. Time for questions. Yeah, Julius from Exma Optics. You are muted, Julius.
Hello, can you hear me?
Hello, now we can hear you.
Yes, I wish to know what is the cost of anti-reflection coating, and also what is the cost of hafnium deposition?
Hafnium is a very easy precursor to deposit. It would be similar as titanium oxide. This is very, very easy oxides to process. The cost would really depend on the complexity of geometry that you want to bring. Comparably to ALD, you only would count the thickness, a number of wafers. In our case, it's a thickness, it's a complexity of geometry, a number of areas that you want to code. So it depends case by case, but we are happy to discuss that with you. And we count mostly by man hours engaged and the equipment time.
So anti-reflective coating on the area of 100 millimeters square is how much?
I cannot tell you right now.
Oh.
I would I would like to suggest that we talk after the event, then I can give you more precise number.
Okay.
Yeah.
Thank you for the question, Julius. Any other question for Maxime? Yeah, Sakin from Abiak.
Hi, am I audible?
Yes, I can hear you.
Good evening or good afternoon. What I want to know is like this is basically a deposition mission, right? As a whole, if we can consider that, like atomic layer deposition, an ALD, which can where we can print kind of our ICs, if I'm not wrong.
You can say this, but we cannot make complete IC yet. That's how
we can just get the design done here, or else how we can collaborate. Could you explain me like little more like what this device does apart from deposition? Yeah.
Yes, you can bring your design. We need to evaluate how complex your design, but basically that's the possibility. Yes.
Okay, so so only deposition does, but not the etching, or else will there be features of etching as well?
Etching is also available, but only for few materials, because we just recently demonstrated we can do etching of zinc oxide at this moment. We test in other material like titania or alumina etching, but it's not available yet.
And there was also one more mission, like this deposition can be deployed in the CAD file as well, right? For a digital note and the checking for the inspection.
Yes, it's possible, but we prefer STL or the file like typical for the photomask DXM, or I don't remember which one.
Like will it be updating on a real time when it is being deposited, or else is it later? Are there real time updates for the CAD model as well?
Yeah, it's possible. Yes.
Okay. Yeah. And may I know like how can we collaborate, or how does the costing start to use or lease the device? Like how will that work?
It's really depends on the ambition you want to implement, and I think it's one-to-one discussion. It depends on the complexity of the project phase. If we need to run, let's say, if you just want to try, it would be one cost. If you want us to do the full development, it would be another. We have now a few customers that ask for contract manufacturing. They'll have like 1,500 devices to be manufactured. This would be absolutely different cost. So it's really depends on what your wish is. Yeah.
And where would you, is there a platform like where we can develop this, like the HDL or physical design part? Or else should we just give you an abstract and you people will develop it?
I think let's move with the abstract, and I think we can review and then give feedback to you on this.
Sure. Okay.
Mm-hmm.
Thank you, Mr. Makim.
Please reach out to me by email, and I would be happy to discuss with you details.
Sure. Thank you.
Thank you.
That's a great product as well. Thank you.
Thank you for the questions. I saw Jens raising the hand from Deal Defense, but I don't know if you still have any question. Well, if not, thank you again, Maxime, for nice presentation and discussion. And I will also put you in contact with this couple of persons that made you a question, so you can discuss by email later on.
Thank you.
And I would like to introduce our next speaker. It's Ravi Kiran Saripali. He's senior researcher at the TII Institute in Abu Dhabi, and he's going to will make a presentation about collaborative solutions and industry engagement for epsilon near zero thin film in photonics. So Ravi, the floor is yours. Feel free to share your screen.
Hello, everyone. Thank you very much to EPIC, in particular, Antonio, for this opportunity. I will be presenting a use case, an R&D use case to the industry. And this particular event is a unique event, I feel, because it connects photonics industry with material science, so which I don't think has happened too often. So I think this is a great opportunity for us. So the first two speakers, both Philip and Maxime, spoke about like oxide thin films. And our requirement at TII is a particular thin film, oxide thin film, essentially, which I will be presenting. So just a bit about TII before we move ahead. So we are based in Abu Dhabi, and we are very glad that we are part of the EPIC organization, because we learn a lot from the European industry, which is quite mature, and we are trying to grow our R&D base in Abu Dhabi. So our company was founded in May 2020, and we are currently around 1,000 employees from various nationalities. So we grew quite fast. We are spread across 10 research centers, and some of the Falcon LLM, as well as the Autonomous Racing League, are some of the things that our company is popular, and you can Google what we do there. With respect to EPIC, our engagement from the last 2 years is in terms of delegation visits to Abu Dhabi, that we collaborate with EPIC to bring the European society here to showcase what we have and to discuss opportunities and like what we want to do, as well as like business opportunities or collaborative opportunities. In fact, from the audience, Ascent Optics, Taras, and Litium Amir, I think, were present in 2 consecutive years. So I am a senior researcher at the Directed Energy Research Center. And what we do is all the way from electromagnetics, acoustics, and high-power lasers and advanced photonics. So yeah, without further ado, let's move in. So straight to the requirement. What we require right now is high-quality indium tin oxide thin films with a sheet resistance varying between 1 to 20 ohm per square. And why we need this? We want heavily doped semiconductors, essentially to bring the real part of epsilon to the visible wavelengths, visible or infrared wavelengths. So I will go back a little bit into our requirement, but the motivation behind this is a field of photonics which is not yet in the market, but we feel is something unique and something right now in the R&D stage, but something that can allow for all optical light processing, is the field of epsilon near zero photonics. And for the epsilon near zero photonics, so essentially what it is like if you, in a Drude model, if you, there is a particular frequency where, known as the plasmon frequency, where the real part of epsilon goes to 0, which means that the refractive index goes to 0. And so the interaction of light at this wavelength with these thin films is quite unique. And I will show a few examples in the next slides. And this plasmon frequency itself depends on the number of charge carriers and what kind of charge carriers we have. And this is why we need highly doped semiconductors, such as indium tin oxide or aluminum zinc oxide, for that matter. And this is a particular example in the figure. Let me just get in the figure where this is a film with 300 nanometers thickness of indium tin oxide on a glass substrate. And when you do reflectivity and a transmittivity study, we see that the real part of epsilon comes to 0 at around in the infrared wavelength, which we can access in a photonics lab. So for metals, the plasmon frequency is about 10 power 15 hertz, which is much greater than the optical frequencies. Whereas for highly doped semiconductors with the advanced technologies, we can bring these to wavelengths which are achievable in the lab. So I will present what we do at the Directed Energy Research Center a little later on. But there was one particular company which used to sell these thin films, and when we approached them, they no longer sell these. So our approach for this meeting is to connect with the industry to see if there is any interest in and capability to grow these kind of thin films with high carrier charge concentration, with high transparency, which we can use for our R&D. And so a little bit more about why these the epsilon near zero photonics is exotic, and why the light matter interaction at these wavelengths is exotic. So when the real part of epsilon goes to zero, which means that the refractive index goes to zero, so the group velocity becomes zero. And this leads to some enhanced light matter interaction. And also the phase velocity becomes infinity. So there is a decoupling of the electric field oscillations in time. So this actually is the main interest of why we want to use these films. And there is there are several studies in academic level studies right now where they show electromagnetic tunneling when you operate, when you interact these thin films with a particular wavelength of light where the epsilon goes to zero. The nonlinearity in these films is enhanced, especially the chi3 nonlinearity. So if you look at this equation, the N2 is the Kerr nonlinearity, and it is inversely proportional to the real part of the refractive index. And when that goes to zero, the N2 goes very high. And this was shown in quite recently in AZO films as well as ITO films. And what we have shown also is some sort of spin orbit interaction. So when you incident these films at that particular frequency or a particular wavelength, and with a spin angular momentum, so you use a quarter wave plate and you convert your linear polarization to either left or right circular polarization. At the output, we were able to see vortex beam generation. So you're able to see spin to orbital angular momentum conversion. And so these are some examples of how you can do all optical processing in epsilon near zero photonics. So coming back to like what we want to do at the Directed Energy Research Center. So we want to use these platforms for to study spin orbit interactions, mostly low TRL R&D. High nonlinearity and terahertz generation is some particular use cases of these films. There are particular use cases where you can use these thin films to generate optical isolators or absorbers. By the way, you can interact the electric fields from different directions. And they've been shown to be integrated easily with meta surfaces. So you can use meta surfaces in tandem with these thin films to do all optical processing. And the most interesting part is, of course, these are CMOS compatible, enabling on-chip integration. So that leads to an opportunity for a new material for on-chip integrations. And what we have at TII right now is a versatile platform where we can achieve any particular wavelength through nonlinear frequency conversion. We can study the wavelength. We can do pulse modulations. We can also do polarization measurements and spatial mode measurements. And so if you have any particular use case where you need a particular wavelength to study a light matter interaction, please feel free to reach out to us and we'll be happy to discuss in further. So yeah, I was given like 8 minutes, I think. So that's it. And thank you for your attention. I'd be happy to answer any questions you may have. So
thank you very much, Ravi. Again, we have time for questions or comments. Yeah, David from Nanovation.
Hi, a very nice talk. Yeah, I'm one of the founders of Nanovation. We're a company that makes oxide semiconductors. And so I think we might have the ability to dope AZO and also gallium oxide to these very high levels that you're looking for, if you're interested. So, you know, we're one of the EPIC members, so you can find us, nanovation.com.
Okay, glad I could reach out to you, David. So we'll keep in touch, definitely.
Thank you, David, for sharing your expertise. Any other question or comment to Ravi? I would perhaps like to ask you, Ravi, regarding the characterization for
Yes.
to obtain the permittivity. Which technologies have you tried up to now, if any, or
So,
how are you looking up to now?
Okay, so we don't do any thin film manufacturing or characterization, and that is where we want to rely on the industry. So what we do is essentially, maybe Taras will talk about it later on in his talk. What we want to do is reflectivity and transmittivity measurements from which we can extract the real and imaginary part of epsilon with different wavelengths, and then we will know at what particular wavelength the real part of epsilon goes to 0. So this is the preliminary characterization that we want to do. And of course, we can also, so we can study the carrier charge concentration, sheet resistance, thickness, and all of these are the basic characterizations that we would require. Yes.
Okay, good. Just curious if you try already any technology in particular, or and you discard because it was not suitable for your material, or if you are looking for somebody from scratch, let's say.
We are looking for somebody from the scratch who can grow these materials, good quality ones, because it's not an easy material to grow. As I understand, I'm not an expert in thin film growth, but because you need very particular vacuum conditions, and so yeah, it could be something challenging to get such high carrier charge concentrations. So this is, I think, something.
Good. Anyone else want to share expertise or have any comment for Ravi? Yeah, Mihai from Hailase.
Hello. Have you thought about non-transparent materials like silicon? I mean, they are non-transparent in the visible spectrum, but they are transparent in infrared. For example, the standard crystalline silicon will have a negative refractive index, or the real part of the refractive index, around 2 micron, from 1.9 to 2.1. So have you thought about using just pure crystalline silicon?
Thanks for the question, Mihai. This is, in fact, like something we were looking into. We can definitely access these labs at our lab, this wavelength at our lab. So it would be something very interesting for us, but we don't know how to grow these thin film silicon or any other material. So yeah, this would be interesting.
Yeah, I'm referring about wafers, like bulk wafers. You can purchase these instead of ITOs or other materials.
Okay.
So you try it with these ones.
Yeah, we will definitely look into that, Mihai. Thank you. Yes, IR is good for us. Yes.
Good. So thank you, Mihai, for the question, and thank you very much, Ravi, for a nice presentation and for showing your needs to the photonics community. And I would like to introduce now our next speaker. So let's go with Marcello Vinetti. He's Senior Scientist for Novel Applications at Lightech, and he's going to present the optical metrology and navigation system for FEOL processes. So Marcello, the floor is yours.
Yes. Thank you very much. I'll try to share it. And I think that should be it. So optical metrology.
We don't see the presentation.
You don't see the presentation. So let's try to share it again. Now probably you see it. Yeah, okay. Yeah. So I was saying optical metrology. Why do you need it? The idea is to show you that the system are so complex that you actually do some kind of navigation system for front-end offline processes. So why do you need metrology? Well, ideally, all processes should be uniform. So wafer to wafer, and wafer chip to chip level, run to run level, and in space from system to system and fab to fab. But actually, neither the world nor our processes are uniform. And so the metrology helps you narrowing variances and navigating toward consistent processes and devices. And this is basically what LATEC can do for you. LATEC is an optical metrology company, and we are producing optical metrology for in situ monitoring. And we are based in Berlin since 25 years, a spin-off of the Technical University. And there are some data about our history and our part of this dynamic group. The business, as I said, is process-integrated optical metrology. The particularity is that most of our sensors actually do work during epitaxy or etching. and also in between as a mapping station in between. Markets are semiconductor and material industry and academia, and they include lighting, laser, photovoltaic, and glass coating. Now, a look at a product manufacturing chain of semiconductor, you see that there are several steps, and in these steps you incur cost, you can produce value, and you also have some risk or opportunities. For example, if you look at starting from the substrate to the epitaxy, that's the first step, you get lengthy processes and high costs because you go from wafers to wafers with the device, planar device on top of it. And here you have high value generation, and you got to keeping under control both temperature, thickness, and the composition of the materials. One thing that you don't know after you finish the epitaxy is how uniform it is, the distribution of these characteristics on the wafer, and then also after that you go to go some other steps like etching, for example. You can again maintain or destroy values typically if you have a wrong etch step point. So for this reason, to control all of these steps, we proposed and we implement our in-situ methodology in ex-situ mapping, in-situ methodology, which is at the level of the front-end epitaxy, ex-situ mapping between different epitaxy steps, and also, again, in-situ methodology during etching. And this is what we propose as a concept of connected metrology. So gather information throughout the front-end line of the processes in order to understand better what's happening to your needs. And let me discuss this in particular with an example of GaN-on-Si end production, where we show how it is possible to control to a very high accuracy film thickness during MOCVD and etching. So basically, there are two main type here of devices. One is this D-mode HEMT, which is the one that I show here, where you have to start with a GaN buffer to do strain engineering directly grown onto the silicon. Then you grow an intrinsic GaN channel layer, and then an argon barrier. And this would be now the D-mode HEMT, high electron mobility transistor. If you had another step on top of it with the P-GaN gate, then you get an E-mode HEMT device. This difference between E-mode and D-mode is this is enhanced mode, the other one is depletion mode. And I'm not going into the details here, but actually you want most of the technology now is going toward the E-mode because it allows you to produce transistors that are normally off. For cost reason, these are grown on big silicon wafer, 200, 300 millimeters diameter, and then extreme uniform AP and etching are required. So the optical in-situ control at that level of half a nanometer, basically one atomic monolayer, is a must. Let's take a look at the MOCVD. You see the animation on the right side of the screen. Our tool is typically is the one that you see at the bottom left side of the page. Is what we call latex epigravity. We are measuring, and this is inserted. This is embedded in a reactor, in a MOCVD reactor. This is typically measuring every about 2 seconds temperature with multi-wavelength reflectance and local curvature on the way of the wafer. At the center of a specific wafer or a radial, and also we can also do a radial scan across the wafer. This would be the center of the specific wafer. As you can see here, the wafers are rotating typically under a viewport, and we measure to the viewport. The in-situ measurement is highly sensitive to, and this sensitivity is a constant from the first layer to the last layer of a typical growth times of hours. So layer-specific deviation can be detected then in real time and in the process, and then used to do advanced process control. But there are some drawbacks like limited accuracy for very thin thermal layers and the fact that you cannot read it to the scans. So what we can use to overcome this is doing post-AP wafer mapping, like with another of our tools, which is the EPIC system mapper. It has several characteristics as you can read here, and then in the slides that you will be receiving afterwards. But the main thing that I want to concentrate now is the accurate measurement and fit of UV reflectance of these product layers. Why this is important? Because if you're looking either at D mode and then also at E mode devices, you want to determine very accurately the argon barrier composition and thickness, and this is usually done now exceeded with photoluminescence, which is not as accurate as our reflectance measurement, because the reflectance measurement, is measuring the argon barrier, the whole of the argon barrier. And so that's, if we do UV reflectance fit, we can get both the composition and the thickness. And the similar results we can also get on the EGAN devices, on the E-mode devices. Here there is the problem that the EGAN on top is absorbing some light, and so it's reducing the capability, the measurement capability of the photoluminescence, for example. That's why it cannot be used in this case. But since we know from the AP how the wafer is structured, then we can join together this measurement before and after the AP, and then get to a very high accuracy in this in determination of thickness and composition of this crucial layer. And last but not least, the etching and endpoint, as I was mentioning earlier. Standard way would be to do optical emission spectroscopy, but this requires edge-stop layers, which is only sensitive to the interfaces. Again, we are using an advanced approach with the UV reflectance, and then an example is shown here in the right. This is now the reflectogram that you would measure during the growth of this HEMT device. So you see that there is the oscillation of around 5 nanometers because of the material that's absorbing the light, and then you get the argon barrier, which has a different extinction coefficient, and then again you can single out very accurately the PGAN material here. If you would think of time reversing this kind of interferogram, you would look first at the PGAN layer, and then the argon barrier, and then the buffer. And this is actually what's happening when you are etching the material. And this here is an example of in situ measurement done during the etching of the etch through of an HEMT structure. So at the beginning, we see very clearly the PGAN and argon layer, and then we are also measuring the 3 different wavelengths at the same time, and then we can get information throughout the etching process, and basically we can decide where to stop with a very exact, with a very high accuracy throughout the wafers, throughout the structure, not only when there is an interface there. And so as a summary, I would say that, what we can do for you. Well, we can help you with narrowing variances and navigating toward consistent processes and devices in the round-to-round system to system, in fact, to fab uniformly with our methodology. And what you can do for us is tell us about your challenges and let us work together to overcome them. Now I'll finish with the kind of sales pitch saying that, you can choose latest metrology as your navigation system, and I'll thank you for your attention. And I'm ready to answer your questions.
Thank you very much, Marcelo. We have time for questions. I saw that Maxim's replay a message in the chat. Perhaps you have a comment about your interest in integration of the products in your machines.
Yeah, we actually looking for solutions to be integrated in our tool to do inline testing. Basically, it's one of the capabilities we want to develop. So probably we can talk afterwards.
Yeah, definitely.
Good. I hope it will be a nice start of a collaboration.
Yeah.
Do we
Thank
have
you.
any other question or comment for Marcelo? Well, if not, thank you very much again for your nice presentation about your capabilities. And
Thank you.
yeah, let's be in touch. And I would like to introduce you our next speaker. So we have changed a little bit in the topic. So we are going to move to terahertz technology for contactless electrical characterization of thin films and also 2D materials. And we have the Israel Arnedo, this director at Das Nano. So Israel, the floor is yours. You can share your screen.
Thank you very much, Antonio, for your kind presentation. I hope you can see my slides.
Yeah, everything.
Okay, perfect. So I'm going to start, as Antonio said, changing a little bit the frequency. So we are going to move to the terahertz. And the idea is to characterize thin films and 2D materials with a tool that we call Onyx. Change, okay. We are a small company. The name is Das Nano, and it was founded in 2012. We are located in Navarre, in the north of Spain, and we are 20 people, and most of them engineers or PhDs. We have three pillars, three basic technological pillars: terahertz technology, software development, and artificial intelligence based on neuronal networks. And we are focused on three measurement possibilities: the layer thickness, the electrical properties, and defects or hidden corrosion, for example. For this, for the photonic wall, it's clearly electrical properties, the one that is relevant, and this is the reason why we are going to focus the presentation on this product. We are a small company, as I said, but we have clients all over the world, basically in the United States, in Europe, and in Asia, mainly in China. What is terahertz? Terahertz is just a region of the electromagnetic spectrum. It's located between the microwaves and the infrared, and it has several advantages. One is because it's light, it gives us the possibility to measure in a contactless manner without touching the sample, and in a non-destructive way due to the low powers that we are using. It provides very good spatial resolution below the millimeter scale in the micrometers scale, and it gives a good penetration in the range of centimeters in most of the electric materials. We are working in time, and these are giving us the possibility to extract information in depth. And finally, and no less important, we are in the region of the electromagnetic spectrum where the light is non-ionizing, so it's harmless for humans. With all these characteristics, we are able to obtain the refractive index of the electric materials. We are able to extract the thickness of multi-layer coatings, and we are able to extract electrical parameters into the materials and thin films, conductance, resistance, carrier mobility, etc. And we are able to detect defects or hidden corrosion. We say that we have this technology in different flavors, and the flavor is no other thing than the actuator that we are using to approach an industry. So this is why we have the possibility to see our technology in industrial robots, in collaborative robots, in tabletop robots, and in quasi-manual, depending on the problem that we are solving. And transversal to all of these flavors, we have the analytics, that is a software, basically a big data analysis and visualization platform with a high degree of interactivity. So all the data that you are collecting, it will be represented in the best possible manner that we have found it. So what is Onyx? So Onyx is a terahertz research platform for bulk, thin films, and 2D materials. We are giving you a tool, a system that is able to characterize electrical parameters of your materials. we are doing so in a contactless and non-destructive manner based on terahertz waves. We provide a full surface map and a single point of electrical properties. We do it fast, 12 centimeters square by minute per minute, and with high resolution, 50 microns. And the tool, thanks to our current customers, has been tested in many materials: graphene, many types of semiconductors, ITO, GaN, MBC, etc. The interface is very versatile. It's a clear representation of the data, easy to interpret, analyze, and export. So this is a friend for the researchers and for the companies. And why Onyx? Because what we saw is that there was the microscale world and the nanoscale world. So when you have a wafer, where a sheet of graphene, for example, you have two options. You can choose to be represented this wafer by just single number, and this is what is going to be done with a DC conductivity test. You are going to associate one number of conductivity to the full wafer, or in optical examination, you are going to see just the whole wafer as a number. And we have the contrary. You can use Raman, AFM, TEM, where you have really, really local information in the atomic scale. So what we saw, as I said, is that there is a gap between both possibilities. And this is where terahertz technology, our Das Nano in Onyx system, could fill this gap, because we are providing a full map with a reasonable resolution. Why in your research and development lab? Because you are going to have a tool to help you to develop faster new materials. It's going to be contactless and non-destructive, so you will be able to test any sample independent on the value. Then you could follow your process because it's not going to alter it. It's plug and play, it's very easy to work with. It's accurate. It gives you full traceability of the measurement samples because it has a camera, so you will identify the region where you are measuring. And there is no need for extensive sample preparation. You just put your sample on top of our holder. And why in a production plant? Because the technology is the same. As I said at the beginning, we just changed the flavor. We just changed the actuator. And in a factory, in a production plant, you will be able to inspect 100% of your production if you are interested. So you will be able to detect really early possible errors and improve your quality as fast as possible. So in the end, you have a tool for both the research laboratory to the industrial scale, and of course, in the middle, the wafer production. This is a picture to illustrate a little bit how is our system, how is our machine, how is our Onyx desktop. You have the supply unit, that is this element that you have here, where the light is generated. The graphical user interface, where we interact with the system. And the tabletop robot that is here, it carries the sample holder, where you just need to place your sample to be measured, and the robot head that is here, where the terahertz beam goes out through this position here. And it has also a camera that is located here to see in all the time your sample and the region or the area that you want to measure. How it works? So as I said, we are illuminating the sample with a terahertz signal. The terahertz signal is interacting with your material, your 2D material that is on top of some substrate. And this interaction is getting back to the receptor that we have in the system, and we are able to extract the information we need from this terahertz signal, the signal that has been interacting with the materials. we can measure several parameters in a quantitative way: conductance, resistance, carrier density, carrier mobility, carrier scattering time, refractive index, dielectric parameters, absorb power. So many parameters related with these terahertz signals. And we can also give you qualitative measurements. So we are able to give you uniformity, homogeneity. So it's a tool that it serves you to quantify, but also to have an idea of your production process, to the evolution of your production process. As I said before, we have tested this tool with many materials in different fields. For example, in photovoltaics and in electronics. We have analyzed many types of graphene: CVD, epitaxial, in inks, graphene oxide, nanoplates, carbon nanotubes, and also many types of thin films and semiconductors: ITO, GaN, PDOT, etc. So happy to test your materials with our system. And finally, I want to show you the resolution that we have. We, as I said at the beginning, we are able to achieve 50 micron resolution. So we are able to give really nice pictures like this one of a thin film, where you can see the difference in conductance that you have. This is very nice for a paper publication, for example, but maybe for your industrial quality control, you don't need so much resolution, and you prefer to have less measurement points and do it faster. So this is why in our system, you can choose by yourself the resolution that you need depending on the purpose that you are covering in each of the tests. We are involved in projects and scientific publications. So again, we are open to cooperate, to collaborate with you. Happy to do it. And I would like to show the last slide with an example of one of the projects that we have a couple of years ago. This is it's called GRACE project. It was for the Ampere in Euromet. And we did this project with 3 meteorological centers, companies and universities. And the purpose was to compare the results that we achieve with our Onyx system with the standard of the industry. And we have a CVD monolayer graphene wafer. We measure with our tool, and then we cut it in pieces, and we deliver to all our partners to be measured with other standard technologies. And we did a really nice comparison. And one of the outcomes of this project was the good practice guide that is now available to see how we can measure these type of materials with terahertz technology. So thank you very much for your time. You can contact me in my email address. You can go to our webpage, and we are happy to say that we are trying to give light. We give new light for the industry. Thank you.
Thank you very much, Israel. We have time again. Marcelo, first question for you.
Yeah, thank you for the very interesting presentation, Israel. One question is, you were showing that you can go from, say, 25 micron or a few microns up to 1,000 micron in this lateral resolution.
Mm-hmm.
How do you achieve that, if you can comment on it?
Yes, the terahertz emitter is embarked in a tabletop robot. So the robot moves in the lateral position at a certain speed. And if you are collecting all the terahertz waves that we are emitting, we are able to reconstruct an image with 50 micron resolution, because this is the last step, the minimum step that our tabletop robot can achieve.
Okay, so you leave the focusing, so to say, or the dimension of the spot constant with just a difference in the acquisition time.
Exactly.
Yeah.
The spot size is around 3 millimeters of diameter.
Okay, thank you.
You're welcome. Thank you very much.
Any other question for Israel? Well, in Epic, you know that we have this typical question that what can I do for the others? What can the others do for me? I don't know if there is some component that you are missing in your system, or a supplier that you would like to evaluate. Could be laser source, for example, to generate terahertz, detector, antennas, something that perhaps you are missing, or kind of requirements or requests that you have to the photonics community.
I mean, we have a quite robust system, so we have developed for many years, and for the moment we prefer not to change anything that is working. But happy if somebody in the audience has a proposition on the things that you comment, antennas, laser generation, happy to hear, of course.
As you use antennas, I guess you use femtosecond sources to make the excitation and to generate the radiation, right?
Yes, yes.
Good. So if there is no more questions for Israel, thank you very much for the nice presentation. It was a pleasure to have Das Nano here today.
Thank you, Antonio, for your
And
kind
I'd like to
invitation.
go introduce you now to our next speaker. So we have Daniel Sapereira. He is Sales Manager, Market Segment Semiconductor at Baller Group. He's going to present the Sputnik technologies as enablers for emerging applications in optical sensing and photonics integrated circuits. So Daniel, the floor is yours.
Thank you, Antonio. Good afternoon, everybody. Yeah, my name is Daniel Sapereira. I'm a sales manager for the market segment semiconductor at Buehler Leibold Optics. And today I bring maybe a little bit of a different perspective from the aim of the meeting. Well, we are more enablers of thin film fabrication and characterization. And today we show basically two examples of our sputtering technologies for applications in optical sensing and PICs. A little bit about Buehler first. So Leibold Optics is a part of Buehler, a Swiss company, and we are present all around the world. So we are machine manufacturers for all sorts of optical applications. We have 3 application centers. One in Germany, so where I'm coming from, one in the US, in Raleigh, and one in China, in Beijing. In all of these application centers, we have machines from our portfolio where we can do basically application tests for our customers and do evaluations of machines and do product development and product innovation. We are a total of 650 employees worldwide as part of Leibold Optics. As part of Buehler, we're more than 10,000. And we have more than 3,000 systems installed worldwide for all sorts of applications, from which we develop 5% of our turnover is then invested back into innovation for new products, new developments, new services as well. Now, what exactly do we do? Yeah, we basically add functionality of different types of substrates via an optical coating. We work with applications in ophthalmics, we work applications in precision optics, in emerging applications in semiconductor. And basically, whenever our customer needs to do an optical coating, they come to us for our machines, and we can do that. So we work with all sorts of substrates, rigid substrates, thin substrates, or flexible, so on and so forth. And we aim to give basically more functionality to silicon or glass substrates, for example, for all sorts of applications. And here I actually have a key fact that also giving functionality via optical coating of an architectural glass can lead to reduction of energy via heating or cooling. So this is really not just for in terms of optics, there's the benefit, but also in terms of energy saving. So all sorts of applications regarding the interaction of the light with the substrate. We have machines for sputtering, evaporation. We have trimming machines. So our portfolio is rather extensive among this more than 3,000 systems we have installed. I come to you from the semiconductor market segment, which is a little smaller slice from the Leibold Optics portfolio. And in here is more about integrating optics with the semiconductor. So we try to bring the best of both worlds and bringing them together via integrating optical filters on semiconductor chips. And we can do that via sputtering tools, evaporation tools, or trimming tools. Our applications are listed here. We work a lot with 3D imaging and 3D sensing, which I will show you a little bit more in the coming slides. We talk about lighting and display, so filters for the display technology. Photonic integrated circuits, I will also explain a little bit more. We are also working in RF technology, so in SAW filters, WAV filters, or wafer bonding. And we are recently also starting working more into R&D topics and more into evaporation for 3D coatings and so on and so forth. So you see here a little bit about our product portfolio, but today I will really focus on two main aspects: what we do in 3D imaging, 3D sensing, and what we are working on in terms of PICs. First of all, I would like to explain you a little bit about our sputtering technology, actually, and thank you to Philippe for already showing a little bit of our tool. This was a nice surprise. We have what we call the Helio series, which is a sputtering tool capable of producing the oxides and metals of some of the materials that were already mentioned today, actually. Our tool, and let me put the presenter here. Our tool is basically it's a turntable tool capable of doing sputtering of thin films of multiple substrates at a time, where you have a sputtering station and a plasma station. So if you think of sputtering of silicon, for example, and the plasma activation with oxygen, then that's how we form the oxide, and you form the silicon oxide that is common in the industry. So basically, the substrates are rotating along the turntable, meaning you are producing these films on multiple substrates at a time. You can use all sorts of sputter targets that could be possible, naming, for example, silicon. Germanium was also mentioned. Niob was also mentioned. And you can use additional gases to make all of these all sorts of combinations, meaning, for example, silicon oxide, silicon nitride, silicon hydride. All of these are possible. In Leibold Optics and with the Helio series, we actually focus on 4 different pillars of our technology. So we actually developed the technology. We have a well-proven system from the precision optics, and we are constantly developing it for a lot of applications. And now for semiconductor, we have an extensive knowledge in filter performance and filter manufacturing on substrate sizes even higher than 200 millimeters. So we're actually working also with 300 millimeter machines, and we have a high uniformity across these bigger substrates on complex filters. We work, because we also talk about semiconductor, we also think about developing filters for low particle performance. So we have here our statement to achieve a number of particles sized 160 nanometers or more, so a number of particles below 100. And automation, also thinking a little bit about semiconductor to connect our tool to the fab is also something that we work on and we develop all within the Leibold Optics world. So this is a system that has been in the market for more than 20 years, and more recently in the semiconductor field. And just a little bit on the examples of potential applications we see for the 3D sensing. We talk about proximity sensing that uses filters in the visible region, and this can be done with filters on RGB. And these kind of filters are based on oxide materials, or can be based on oxide materials with niob and silicon, and basically working with the structure, you can build the filter with the different colors. Or if we're talking about applications like infrared cameras or facial recognition, then we're talking more about filters that are built and they build based on silicon hydride or silicon oxide, and with structures that can achieve performance in the infrared. So at Buehler, we developed these so they can be integrated into semiconductor fabrication. So really building these on top of chips. So this is our core in the semiconductor group. And our intention is to really integrate the machine into the semiconductor fabrication, and be that building the films on top of structured wafers, or building the films on that can be structured later on. And this is the highlight of this slide, where you see two different approaches, where both can be where both our tool can be present on. And this was a little bit pointed out by Philippe during his talk. We also have an extensive collaboration with IMEC, where we develop processes, we try to understand particle generation, and we're really trying to bring together the tool into a state where the semiconductor market can also benefit from. So this is a very good extensive collaboration that we've had for a few years now. The next point that I have here is just a little bit of a teaser. We also have a collaboration with a company called Shinkon. Shinkon is a machine supplier from Japan. We have a collaboration with Shinkon in the way that we can promote the products from Shinkon in Europe. And Shinkon aims to revolutionize the photonics industry, and Buehler is helping in this revolutionization. Sorry. And how is this being done? So thinking a little bit about lithium niobate and photonic integrated circuits, there's a dependence on the industry of what is called these wafer bonded lithium niobate films that are used to all sorts of applications, namely in PICs. And actually, Shinkon is working on a sputtering technology that is capable of doing the epitaxial growth of lithium niobate on the various substrates, meaning growing lithium niobate on a film following the crystalline structure of the substrate or the film that is below it. So actually looking into applications of PICs, and working with materials such as lithium niobate, silicon nitride, or silicon oxide for such applications. And we are actually actively promoting this new technology, because we think that we can really revolutionize this field. And we are looking for partners that are willing to discuss with us, talk to us more about the needs of their industry, of their markets. So if you are in this field and you are interested in learning a little bit more what we and Shinkon are doing, and are willing to cooperate, I'm very happy to discuss this further. And this is one of the reasons that we are here today presenting. So this will be my last slide. Thank you very much for your attention. If you have any questions, feel free to ask, or you can contact me at any time. Thank you very much.
Thank you very much for presentation, Daniel. Any questions? I don't see any questions. I will perhaps have a question, because we were talking about metrology also in previous presentations. Do you also implement some metrology tools in your machines to control deposition thickness, quality of the coating, and so on?
Yes, actually, it's a very good question. So if you saw the structure that Philippe presented in one of his slides, you saw a lot of layers stacked on top of each other. So in order to achieve this precision, we integrated to the tool what we call an optical monitoring system, meaning we grow the layers and we measure the optical properties of those layers as we are growing them. This allows us to have a tight control over the thickness of the films that we are building in order to achieve a certain stack. So yeah, the answer to your question is yes.
It's a combination like laser and a photodetector, or a light source and a photodetector, or is more complex than that?
It's basically, you can imagine a spectrophotometer integrated into the tool. Yeah.
We have another question from Mihai from Hilace.
Hi.
Hey Daniel, I'm just wondering how actually this optical control is actually functioning into your system. So for example, you have a recipe, let's say 40 layers.
Yes.
Just put something in mind. And the question now, are you looking to supplement the irregularities in index of the material? For example, if the material itself is not stoichiometric or it moves a little bit lower or higher with refractive index, then your machine will accommodate that in order to match the initial design.
Yes. So basically, we integrate a design of what the filter should look like into our software, and what the OMS or optical monitoring system is doing is adjusting or building the filter with such design in place. If there's a deviation within the process, then the following layers would be adjusted automatically in order to still meet the desired refractive index that is planned, meaning what we call a no-fail batch because of deviations in the process. So yes, this is possible.
Sure. But for example, I come from the laser field, so yes, there is actually a little bit a critical point of the electric field into the films. And for example, if your automatic system it's adjusting just to match the desired outcome, then you actually change. You could potentially change the whole stack structure in order to achieve that design, and that would actually for the laser optic could mean like completely different results in the end. Yeah, you could have like reflectivity or transmissivity, but with a downfall on the laser damage, which will affect this. Okay.
Correct. So it really also depends on the application, because you can always choose to do a fixed stack without deviations via optical monitoring, or in the case of the applications that I mentioned, the optical performance in the end is what governs and is what is the most important. So these deviations can be accounted for. But you're right that for laser optics, the situation is a little bit different. Yeah.
Okay, I can imagine that for standard filters in CCD cameras, or sorry, CMOS cameras and such fields, this would actually not matter that much. So just the end result will be more progressive.
Correct.
Okay,
Correct.
Thank you very much.
Yeah, no, you're welcome.
Any other question for Daniel? Well, if not, thank you very much for great presentation.
Thank you, Antonio.
Nice discussion as well.
Thank you, everybody.
This afternoon. And let's go with our last speaker for today. Continue talking about metrology, and it's a pleasure to introduce Taras Lisuski. He's head of business development at the company Essent Optics, and he's going to present the broadband metrology solutions for high-end and quality control of optical coatings. So, Taras, the floor is yours.
Thank you very much, Antonio. Thank you so much. Thank you, Epic, for very tremendous work you do for the whole Photonics community and for bringing all of us today and other days to discuss important topics in Photonics. It's my privilege to be here. My name is Taras Lisowski. I'm taking care of business development at Essent Optics Europe. The topic of my presentation is broadband metrology solutions for high-end quality inspection of optical coatings. A few words about our company. We were founded in 2009. Our office is based in Vilnius in Lithuania, and you probably know Lithuania is a really photonic buzz right now on the market, with a very big number of impressive companies active in optics, lasers, and photonics. We design and build high-performance broadband spectral photometers, tabletop systems for quality inspection of optical coatings. And this is our own one and only business for the last 15 years. We have customer base in more than 30 countries, and the advantage of our company is that we have all the technologies in-house down to the monochromatic level. So we design and build hardware, software, firmware, we run mechanical design, PCB design, optical design, and so on. We cover very broad range of systems and very broad range of wavelengths. We go from UV from almost 0.2 nanometers to 14 microns. And the whole product line from our company is actually divided in two main groups. The first group is those products which are designed to measure transmission and reflection on flats or prisms or cubes. This group of products is called Photon-RT spectral photometers. And we have two main systems. One system covering the range from UV to 5.2 micron, and the second system covers the range from 7.5 to 14 micron. And we also have a product line to measure transmission and reflection on lenses and lens assemblies, like objectives. Here we also have two main products. The one called Linsa 150 covering the range from UV to 1.7 micron, and the second system is focused on mid-wave infrared range. I wish to talk a little bit about each system. So this one, Photon-RT 0252 model, is the hottest selling system from our company. It has a very wide range, can measure transmission and reflection automatically at any angle of incidence with SMP polarization. The polarizers are built in inside. We have a capability to measure very small and very big samples. We are famous for very accurate measurements. The image shows here a reflection measurement of a very fine laser mirror at 45 degrees SP and average polarization. But the main issue about this image is that we don't have any changeovers. Actually, this is the arrow points, the area where we are changing gratings and detectors, and you obviously see no jumps, which are very typical for other systems on the market. We are very famous with this system for the world record broadband range. This record was set in 2019 and is still kept unbeatable. We do cover the range from UV to 5.2 micron in a single system, and the example shows here our capability to measure gold mirror broadband. We take very precise attention and care to routine, typical daily measurements of samples, which fortunately are not taken care by other companies. Take, for example, a case of transmission measurement of a sample at specific angle of incidence. Obviously, you know that there is a beam displacement, which depends on the three factors: sample thickness, angle of incidence, and index. So the beam is displaced, and none other system is capable to track this beam. What we do, if you look into this blue dot, this is a symbolic image of our detector. We actually move detector to catch the beam, and our detector is capable to track this beam all the way with the change of the angle of incidence. And this feature helps us to measure even polarizing cubes at different angles of incidence or semi-prisms. The image on the right hand side, you can see transmission measurement of SP and average polarization of the cube from 0 to 20 degrees with a 1 degree step. We see a growing demand for measuring of optics and coatings optimized for space applications. Example here shown the so-called multi-zone filter, which represents a very sophisticated design. Actually, a number of individual bands or filters attached one to another or coated all together. They are all different in dimensions. We are capable to measure them fully automatically. We actually map them out automatically in our system and measure them automatically. The example here shows an image where one of the bands was just 700 microns in dimensions. The same stage, which is shown here, is used for characterization of linear variable filters. We teamed up with a company from States, Amigo Optical. They were very cooperative and supportive to provide us with a few very nice samples, and you can see the results of the tests of these samples. We moved to long wave infrared last year. This system is grating based, is not FTIR. We cover the range from 7.5 to 14 microns and is designed for transmission and reflection measurements at different angles of incidence and polarization of coatings and samples with coatings optimized for long wave infrared range. We even can measure very thick samples at different angles and also compensate for beam offset while measuring transmission. Lens measurement technology is a pretty new one. We had a few cases from our customers saying that, okay, we want not just see the results on the witness piece, but on the real lens. And we want to see transmission and reflection of lenses, and we want to see reflection from different parts of the lens. And we have different lenses like convex, concave, spherical, aspheric. So the whole set of different challenges which the customer has posed to us. We have this technology and we have managed to develop a system capable to measure transmission and reflection from all that types of lenses. And the examples here show reflection measurements of convex and concave lenses at different points of the lens surface. All these procedures are also being done fully automatically. This system represents our challenge and results for measuring of lenses and complete lens assemblies for mid-wave infrared. The advantage of this system is that it's capable to measure fully assembled objectives or telescopes with an end-to-end dimension up to almost 700 millimeters. This part of my presentation is related to a very new product, which we will be showing this year. We see a trend of measuring ultra-narrow bandpass filters, so-called nano-band filters, or cutoff filters with extremely steep edges and coatings with high optical density. In fact, all that challenges, what we see, are not met in full currently with the metrology industry. We worked on that system for the last 2 years, and we have managed to design a system which is focusing on the coatings optimized for LiDARs, for fluorescence microscopy, laser safety, telecoms, space exploration, defense and security. This is a broadband tabletop system with a very wide range, with an extremely high spectral resolution down to 0.06 nanometers. We are capable to measure optical density up to OD8. Filter bandwidth can be as small as 0.1 nanometer, and slope steepness can be also as small as 0.02%. A few examples demonstrating our results, recent results. The image on the left shows our capability to resolve mercury emission lines, which is a yellow doublet. And the images on the right show real measurements of ultra-narrow bandpass filters for visible range and for near infrared range. The upper image, we have full width have maximum like 0.42 nanometers, and the image below has the filter has full width have maximum at 0.7 nanometers. The high OD measurement capability was also confirmed. This filter has extremely high OD, and we were able to measure up to OD8. That's a lucky coincidence that tomorrow we'll be showing this system officially at Optotech in Frankfurt. So if you are around or plan to do so, please stop by our booth. We will be very much happy to show you the instrument and make some tests as well. Finally, 2 questions which are EPIC famous for. What can we do for EPIC members and what can EPIC members do for us? First issue regarding our capabilities. We believe we foster advanced research for the companies which make coatings or make research on coatings or use coatings for advanced applications. And we help bringing cutting-edge coatings to market. Obviously, you cannot produce any better than you measure. And metrology is that last mile where the quality of your coating depends really on the accuracy of your metrology system. And what can EPIC members do for us? We are looking for more reference standards which can independently qualify our systems. And we are also looking for a cooperation with the coding companies or companies from photonics field, which can provide us with extremely challenging codings, so we can test our systems for ultimate performance. And as a result, bring better codings to markets altogether. That's all from me for now. Thank you very much for your attention. I'm very open for questions. Thank you.
Thank you very much, Taras, for nice presentation of all your capabilities. We have time for questions for Taras. I have a question regarding the system that you presented, where you can measure the whole optical system. What's the size they can admit inside? Or can you work in also customized solutions if somebody has a big optical head, for example, that need to be characterized?
The smallest sample we were able to measure as standard was like 4 by 4 millimeters. The biggest size was 150 millimeters. But for that sample, which was mentioned for space application, the actual dimension was 700 microns. So we were able to generate a beam spot on that sample as small as 400 microns. And we were able to measure these narrow bandpass filter extremely well, surprisingly well, to be honest.
Good. And what was the main challenge when measure these really short band filters? Is more the detection part, or it's also the emission that it must be really a combination of accurate detection and emission to measure the filter?
If we talk about nanoband filters, the resolution of the system is the main priority. We need to have a very high resolution to be able to characterize that narrow bandpass filters and the steep slopes. As for this application for space, the challenge was that these filters are not standard. So each one comes in an absolutely individual design. So now when we take the sample, the system doesn't know what is going to measure. So we came up with the idea that we first map out the sample to understand how many zones are on the filter and what are the physical dimensions of the zones. And then with a second scan, we measure each zone in the center and qualify each filter sequentially and automatically. That really saves time a lot. It's a totally time-killing procedure for any other system.
Nice, very nice. I see a question from Silicon Australia, Standui.
Yes, please.
Thank you very much, Taras. Nice talk. 2 questions. The first is about the beam divergence from the system, and also you mentioned that the size of the wafer, the size of the sample is maximum around like 150 millimeter, right? So this is the maximum of the area that the beam can map, or really the wafer size?
Okay, let's start from the first question. For our broadband system, the beam divergence is like ±1 degree. And for the newer system, which will be shown tomorrow at Optotech, is ±0.2 degree. So very narrowly collimated beam. And for your second question, no, this is the maximum sample size which we can handle, can put and measure. We do have so-called XY mapping stages, which are capable to map out the sample, and they have open area like 40 by 50 millimeters and 40 by 110 millimeters, 2 different stages. And you can map the whole area automatically.
Thank you. Yeah, because we're working on 8-inch mean 200 millimeter wafer sizes. Yeah. For the measurement, we don't want it to, to cut the wafer. So it would be nice if the system can reach to 200 millimeters wafer sizes.
Unfortunately, we cannot handle this. We do have a few requests from customers because they are going to bigger wafers, obviously. We're thinking about that, not ready yet.
Thank you. Appreciate it.
Thank you so
much. Looking forward to the update. Thank you.
Thank you, Tandui. And if there is no more questions, I want to thank you again, Taras, for a nice presentation, and good luck tomorrow at the show. I hope that you have a lot of visitors.
Thank you, Antonio.
And I would like to steal 2 minutes more of your time so I can introduce you Joan Priol from Physics, that they are also working in the metrology world. So Joan, you can share your slide and talk a little bit about your expertise in metrology.
Can you see the slide?
Yeah.
Okay. So at Physics, we also do metrology, of course, but we do wavefront metrology. So the challenge I wanted to talk about is kind of related to what Taras was talking about, those very narrow bandpass filters. So once the thin film is applied, once they are coded, there is some requirement to test the transmitted wavefront error and the surface error of those optics. So Physics has developed two solutions to measure those type of surfaces or transmitted wavefront error after coding is applied. So the first one, we call it the Kaleo multi-wave. So it's an instrument that can integrate up to 8 different wavelengths, and it's used like a piezo interferometer. So we do a double pass measurement that's going to give us access to the wavefront aberration. Another solution that we've been developing is modular approach. So we have one wavefront sensor that allows to accommodate a broad wavelength range. And then we can integrate multiple wavelengths and swap them. Then we can shape them to adjust to the size of the optics we want to test. Could be from a few millimeters all the way to 200 millimeters. So what we do, we measure the wavefront at different wavelengths, or at the wavelengths of choices. So if the filter is only transmitted at a specific wavelength, we can pick the wavelengths and perform the wavefront measurement at this specific wavelength. On the other side, we can also measure coated surfaces. So if the surface is designed to reflect at a specific wavelength, we can perform the surface qualification at the specific wavelength once again. And lastly, the measurement is not polarization dependent. So we can either do multiple surface or transmitted wavefront error at various polarization in order to access those type of parameters. The available wavelengths, we cover UV to long wave infrared. So I'm not going to go in all the details, but we have different wavelength sensors that cover the whole wavelength range from 193 all the way to 10.6 microns. And we can integrate also tunable lasers. So if you need a very specific wavelength, we can find a laser on the market that we can integrate in our test instruments. So what's the wavefront measurement we gave? Here's an example: transmitted wavefront error on the space qualified filters that was designed to transmit only around 7 and 80 nanometer. Here's a measurement of coated surfaces that we tested at 3 different wavelengths. And the last example here, we did some measurement on polarizing thin films. So the idea behind this was like, does mounting the polarizing thin film in its mount would impact the wavefront error that will ultimately impact the imaging quality? So that's in one slide what we can offer at Physics to help coating manufacturers qualify the optical function or the surface of the optics they are coating.
Good, thank you very much, Joan. And you can perhaps type in the chat your email address in case somebody wants to reach you. You have your email address. And thank you for this presentation about your capabilities. So it's we are reaching the end, and it's again time to say thank you to our sponsor. So thank you again to Spectrogon for being the sponsor for today. Thank you, Herman. You have also in the chat his email address for any question, doubt, or request. Please feel free to reaching him or just contact also me, and I will introduce you to him. And thank you everybody for the nice discussion today. I really enjoy the topic. Really very interesting presentations. Thank you to IMEC and Ravi from TII for presenting some on the one hand request, and also what are they doing now, and also to all the other speakers, Maxim, Taras, so I forgot a few names, Marcello, of course, and Israel, for presenting also the capabilities of their solutions. Thank you very much for being here today, and I hope to meet you in the next EPIC meeting, on site or online. Just check our website to see which topic is more interesting for you. Thank you, and good afternoon, everybody.
Thank you.
Thank you. Goodbye.
Thank you, and bye-bye. Thank you, everybody.
Thank you. Bye-bye.
Thanks a lot. Bye.
Thank you. Bye-bye.
Thank you.
Thank you. Thank you.